All right, let's get started. Two quick announcements. Number one, we're going to be having a barbecue in Crystal Lake on September 28th. Hess Pels will be providing a lot of the food. We'll provide all of the meat and like vegetarian versions of the meat, and so we're counting on you guys to bring stuff like desserts and appetizers and drinks. So I'll be sending out an email and probably a doodle attached to that with like a sign up for if you guys can bring stuff. Not everyone has to bring stuff, but everyone who does, the more people who do it will make it better. So the other announcement is Joy sent out information about APEC 2014 about Student Travel Support Awards. So this is a power electronics conference, so not everyone will be interested, I guess, but I'll attach it to the back of the sign-up sheet so you guys can take a look if you are. All right. So our first speaker today is Shamina Hossain. Shamina is a second-year master's student under Professor Thomas Overbye. Her current research is focused on developing fault location methods for distribution systems, and she received her BSEE from Washington State University in 2012. Shamina.
Should I maximize it? Okay. All right. Hello, everyone. So again, my name is Shamina Hossain, and I'm under Professor Thomas Overbye. And today I'm a second-year master's student. And so today I'm going to be presenting on distribution fault location using wide area voltage magnitude measurements, which is a project I did with Dr. Overbye and Dr. Hao Zhu. And so first, a little background. So with the Smart Grid initiative underway, there's a big push for increased situational awareness. And as a result of this, there's many devices and systems that can take fast sampled, localized measurements in near real time. And of those measurements, such as voltage magnitudes. And so traditionally, for say, fault location algorithms, both current and voltage measurements were used. And these measurements are often made at the substation end of the feeder lines. But now with these localized measurements, we can get these, say, like voltage magnitude measurements from anywhere on the line, which motivates an algorithm that only uses those voltage magnitudes, reducing the amount of data that we need to process because we're ignoring current entirely. And so today I'm going to be presenting on an iterative simulation-based fault location algorithm for distribution systems. And so given a model of a distribution system and the fault type and fault phase, I'm saying that from the voltage sensors that are placed across the network on all along the lines, I would get a measured voltage profile given that a fault has occurred, which could be at the control center. You could be notified by sudden changes in voltage. And so once I get that measured voltage profile, in each iteration, I will simulate a fault on a certain location with certain impedances of the same fault type and phase, and compare these two profiles using the Euclidean error norm criterion. And using that norm, I will find the best match between the two and thus find my location and impedance of the fault that has occurred in the system. So for the rest of the presentation, I'm going to be using this 13-bus feeder system from a Power World case. And it's comprised of 13 buses, 10 loads that are primarily residential, industrial, or commercial, and with a 13.8 kV feeder line. So the first component of our algorithm is obtaining the measured voltage profile from these voltage sensors that are placed all across the network on the lines. And so looking at the feeder system before, we're assuming that there's a voltage sensor placed on every bus, and so for a total of 13 sensors. And given that it is in faulted condition, this is the measured voltage profile that we would receive, or a sample one. And so once we have that measured profile, for each iteration, we need to obtain the calculated voltage profile. And this profile is obtained through a simulation program, such as PowerWorld, which is what we use for this paper. and obtained for a certain fault type, so single line to ground, line to line, three-phase, and so forth, and of course in phases A, B, or C. And the impedance range would depend on the system that you're looking at. And so for the feeder system, the 13-bus feeder system, we would have a total of 156 different combinations of fault phase, fault type, and fault location. But for our algorithm, we're assuming that we're given the fault type and the fault phase. So it greatly reduces the amount of simulations that we would actually have to go through to check which one is the best match. So here are two sample calculated voltage profiles. The leftmost one being a balanced three-phase fault on bus 7, phase A with impedance of 5 ohms. And the rightmost one, a balanced three-phase fault on bus 12, phase C with impedance of 25 ohms. And both of these were achieved using Power World. And so once we have the measured profile as obtained from the network and a simulated profile for each iteration, we're going to use the Euclidean error norm criterion to compare the two. And so the norm value that we get, the error norm, is then going to be checked against a threshold value, which has been derived from the highest measurement error accuracy noise. And if the resulting norm is less than that threshold, we have deemed that we have found the best match and that the fault location and the impedance has been found. So to demonstrate the use of our algorithm, we can go through a Power World case study using the same feeder system presented before, the 13-bus system, and the measured profile voltage, which we're assuming the feeder system had at least one voltage sensor on each bus. And so given these two, we're also given that a balanced three-phase fault in phase A has occurred, putting the system in a faulted condition. And the fault impedance is deemed to be a maximum of 60 ohms, as determined by typical fault currents in distribution systems, and incremented by 5 ohms in every iteration. And then lastly, the threshold value is about 0.05. I did a balanced three-phase fault. Okay, no phase A. So for each iteration, we'd be going through, the iterations would look as followed. First, we'd have a balanced three-phase fault in phase A on bus 1 with 0 ohms, then 5, 10, and so forth until the best match is found. And the last possible simulation would be a balanced three-phase fault in phase A on bus 13 with 60 ohms. So as an example, we can go through the second iteration. And the second iteration is a balanced three-phase fault phase A simulated on bus 1 with an impedance of 5 ohms. And so the following, the shown calculated voltage profile would be obtained from Power World. And so now we have the calculated profile and the measured voltage profile. So by comparing the two using our Euclidean error norm criterion, we find the norm to be 0.44, and we perform the check. Is it less than our threshold of 0.05? And we find that it doesn't satisfy the condition. So we move on to the next profile of with 10 ohms and so forth. So it is found for this particular case that the matching condition is satisfied in the 80th iteration when the balanced three-phase fault in phase A is simulated to have occurred on bus 7 with an impedance of 5 ohms. And the norm is 0.02, which is yes. It's below 0.05. And a visual comparison of the two profiles are shown here. And so to reiterate some of the benefits of using this fault location method only using the voltage magnitudes, one is, of course, it reduces the amount of data that we're processing. And these localized measurements that are fast sample allow us to have a great availability of data. And so in the future, we plan on testing this like on real data and also on a larger network that's more realistic. And also, since a fault doesn't just occur just on bus 1 or bus 2, but where on the lateral it occurred according to our impedance values. And lastly, right now there's a big computational burden in that we have to go through every iteration, every fault location and impedance value to get to our fault. So if the fault occurred on bus 200, we'd have to get through all of those to get to there. And so right now what I'm looking at is using the golden section search routine. And the golden section search routine is a technique for finding an extreme minimum or maximum, and by successively narrowing down a range of values, a range by looking, by successively narrowing down a range to find our extreme minimum or maximum. And so in our case, this would now be, after we obtain the measured profile, we can use the golden section search routine to select the range starting and endpoints, and as well as the probing locations. And then this is selected by using the Euclidean error norm criterions. And so only those locations selected by the golden search routine would be simulated, greatly reducing the amount of simulations we'd have to go through. And so for one of my preliminary tests, I looked at the same feeder, the 13-bus feeder system with a fixed impedance. And of the 13 possible simulations that could be made, only 5 were needed, and the solution was found in 6 iterations. And so, for the future, I'm going to be working on making a MATLAB Power World interface where my Euclidean norm and golden section search routines would be performed in MATLAB, and it would call Power World whenever the simulations were needed. And thus, a user can input the measured data, fault type, fault phase, and get their fault location in the end. So, any questions? Yeah?
Did you run into any hiccups or anything that caused you to pivot, like as you were doing this project? Something that you found out maybe you couldn't do, or?
I'm finding, like, as I'm going more into the golden section search routine, I'm finding like one of the strict conditions for that is that it has to be a unimodal function, so that, you know, before the fault, everything has to be minimizing towards that and increasing after monotonically. And so I'm starting to look more like, I think it works for radial distribution systems, but yeah, so that's one of the hiccups that I'm trying to look into further and see like what I could do differently if, say, the golden section search like focuses on a wrong minimum, but maybe I could use a threshold value to check and start over the search in that case.
Yeah. Will you be able to detect the type of fault, because so far you assume that it's a balanced fault conditions, right? So is it possible to detect the type of fault that has happened in the system?
I'm sure there is, like depending on the like maybe looking at the voltage magnitude patterns, but I guess I haven't considered that yet. Right now I'm assuming that it's given to me.
Okay. Because I was thinking that if the fault signatures are not unique, it means that for a specific kind of a fault and for a certain distance location, the signatures, if they are same, let's say for line to ground for a certain distance, and a three-phase fault at a certain other distance, if they both match, then you would end up at a point where you would not be able to decide what the kind of fault and which is the location where the fault is.
Yeah, and that's a good point to consider. I'll look into that. Yeah. Yeah.
Present audience for me actually. So can you say what's the difference of roll-up to other multiplication algorithms that are in the literature?
Well, I found, so of course there are present work that use voltage sag data, as I did, you know, looking at the pre-fault voltage and the post-fault. But all of those, they still use the current data to either update their load models so they can compare those voltages, or I think another one was using a pattern recognition technique. But like all of them still depend on that current value, and actually sometimes pretty heavily. And so I would say a big difference between mine and theirs is I am mostly just concerned with the voltage magnitude, and I'm not even looking at the current.
Probably what you want to say, because some utility people, when we presented this, they said, well, why on earth would you throw away the current? And the answer is we're not necessarily throwing away the current. We have the current, great, we'll use it. Normally you would have the current at the beginning of the feeder, but not down the feeder.
Yes.
So you could say, and probably you want to address it this way, is to say, you can utilize the current, because all your simulations will give you current as well. So current can just be another piece of data
parameter in it.
Match on. But where you're different is you're really depending on the distributed voltage along the feeder. And that's the key added value.
Yeah. Definitely. Thank you.
Do you
Yeah.
find a fault at bus that you didn't get emission from? Could you like, I mean, at the moment you're assuming you're getting all the voltage,
Yeah.
right? Do you think if you were missing something, you could identify?
I'm not. Yeah.
Just
I would think not, but maybe you could say it's between the buses that you are getting measurements from. Like, oh, I think it's between buses 8 and 10, not knowing, not having any sensors on the other buses in between. Yeah.
Probably what you should say is, look, if I've got 1,000 measurements and I missed one, 999 still works pretty well.
Yeah.
If I have only one, it's not going to work that well.
Yeah,
So
definitely.
It depends how, I mean, that's something for you to consider in your research, is saying, okay, how many of these voltage measurements do I need? With the idea that the more you have, probably the better your result. If you look at the limiting case of none or everything.
Definitely. Okay. Thank you. You other? All right. Well,
Good.
yeah. Thank you.
Good job.
So our second Hello. So our second speaker is Uyen. She is a first-year grad student under Professor Overbye. She got her bachelor's degree in Vietnam at Ho Chi Minh University of Technology. And during that time, she joined an exchange program to UIUC, where she spent 1 year here. And right now, she's doing research on the sensitivity of GICs to grounding resistance.
Maybe.
Is it one of these down here? Somebody know?
Oh,
there?
yeah. Oh, I think this one.
There we go.
Hi everybody, I'm Uyen, and today I will talk about geomagnetically induced current sensitivity to the assumed grounding resistance. First, let me introduce to you what is geomagnetically induced current and how does it occur. So the solar storm associate with coronal mass ejection, and this ejection is plasma content composed of mainly proton and neutrons. And when the Earth captures the charged particle, the magnetic field of the Earth change, and as we call this is geomagnetic disturbance. And this disturbance create the quasi-DC current with the frequency much lower than 1 Hz. We call this current geomagnetically induced current. In short, it's GIC. And GIC can cause half cycle saturation in transformer, which increase the harmonic currents and also the reactive demand, power demand. So the earthing GIC, which is GIC flow to substation, are more important to us than the GIC flows in the transmission line because they flow directly through the transformer. And if their magnitude are too high, they can saturate the transformer, which we don't want to. And GIC can be calculated based on the geometric data, means the latitude and longitude of substation, the configuration and the value of the resistance in the network. Although the resistance value of the transmission line and the transformer are usually known with high precision, the value of the grounding resistance may not be accurately available. That's why in our paper we want to examine the sensitivity of the GIC to the grounding resistance. The GIC in the system can be calculated using first the equation V is equal to G to the power minus 1I, with V contained on the substation neutral DC voltages and bus DC voltages. The I is the vector contained on the injected current. I model the vector I model the impact of GMD, the geomagnetic disturbance, in the induced light DC voltage as the Norton equivalent current injection. And all the element in vector I can be calculated using two equations below. So the Vij, I and J are two arbitrary nodes but connected in the system. And Vig is the voltage difference between node I and node J. Rij is the resistance of the transmission line between node I and node J. And and from that we can calculate the element at position I of vector I using is the sum of all the current flow into the vector I. G is the matrix that is constructed similarly to the bus admittance matrix, except G only contains only the conductance value, include the substation grounding resistance, and the transmission line, which has series capacitance will be omitted, and transformer are modeled with their guiding resistance. Let's look at a case study for this. This is the two substation for bus system, and the geomagnetic disturbance create electric field 1 volt. In this case, 1 volt per kilometer. Two substations are separated by 150 kilometer. Hence, we have the difference of the voltage is 150 volts. The grounding resistance of substation A is 0.2 ohm, and the grounding resistance of substation B is 0.3 ohm. And below we have the equation for the three-phase GIC at substation A. And also B. So we have using the calculation we got the result is 88.26 ampere, which means the GIC for one phase is about 29.4 ampere, and that value agreed with the result of our simulation using the power simulation software. Then we can generalize the equation about in the previous slide to get the equation of GIC at substation A according to the RA, RTHA, and VTHA. So RA is the grounding resistance of substation A. RTHA is the Thevenin equivalent resistance, and VTHA is the Thevenin equivalent voltage looking into the network from substation A. Then we derive the normalized variation, which is the percentage of the GIC as substation I in here, in terms of the percentage of variation of grounding resistance at that substation. And our result is only contain the grounding resistance of substation I and the Thevenin resistance, the Thevenin equivalent resistance looking from that substation I. So we need to know the Thevenin equivalent resistance. Then we can get it from the driving point resistance. Driving point resistance is the diagonal element of resistance matrix, and the resistance matrix is the inverse of conductance matrix G. But note that G should never be explicitly inverted, because in large system, G is usually sparse matrix, And we can find the diagonal element of the inverse of the sparse matrix using the sparse matrix sparse vector method. Then here we got the equation for the Serpentine equivalent resistance at substation I. Now we define scripted R. I is the absolute value of the normalized variation. If the value of R is small, that means the accuracy of the crowding resistance at that substation is less important, and vice versa. In our case study, we have the scripted R of substation A is equal to 0.117, which means that if the crowding resistance of substation A vary like 1%, then the GIC at the substation A will vary 0.1176%. However, if the crowding resistance if that crowding resistance increase 100%, then using simulation we got that the GIC of that substation only decreased by 10.6%, because this is only the linearization about the assumed crowding resistance. Next, we use our algorithm to apply it on the bigger system. This is the 20-bus GIC test system. And in this system, substation 1 had the GIC blocking device, and substation 7 model series capacitor that had no connection to the ground. That's why when we get the information for the, when we get the normalized variation for the for this system, there's nothing about substation 1 and substation 7 in here. In this system, we can see that substation 3 and substation 4 has a significantly higher normalized variation than other substations, especially substation 4, which has a normalized variation 0.802. This means that the accuracy of the crowding resistance of substation 4 is very important to know the GIC. Now we apply this algorithm for real power system with 62,500 buses and 27,600 substations. Is a model of the EI, and only a small number of crowding resistance value are known in this system. So we use a simplistic model to estimate the rest of crowding resistance. And in this model, the value of crowding resistance only depends on the voltage level of the substation and the size of the substation, which means how many lines connect into it. And the soil resistivity is not included in this model. Although in practical, the soil resistivity have a significant impact on the resistance, on the crowding resistance. This is the table that shows us the normalized variation of top 10 substations that have highest GIC in the system. And in this table, we can see that 6/10 of them have the normalized variation more than 0.5, which means that the crowding resistance dominates in determining the value of the GIC. And this is not just in the top, not just in these 10 substations. We saw that like in top 100 substations, the average normalized variation is 0.47, and in top 500, the average value is 0.51. From that, we can see that the sensitivity of the GIC to the crowding resistance cannot be ignored. It's significant. And this is about our future work. So the Thevenin equivalent resistance not just depend on the transmission line resistance and the transformer resistance, but also on other substation crowding resistance. And those values we also not know it accurately. So one approach that was used by Professor Piriola in his paper published in 2008 is he changing the substation crowding resistance by a fixed percentage, either by fixed percentage, fixed amount, or a random percentage in a range like 20%, 100%, or like setting them on to zero as the case of a perfect earthing. And hence, we also researching on this direction. In conclusion, this paper provide an algorithm to calculate the sensitivity of the GIC to the crowding resistance, and the results show that GIC can be depend on the crowding resistance in many cases. And one contribution of this paper, another contribution of this paper is that it provides a method to identify what substation crowding resistance need to be known accurately, and this will help utility engineer to focus on the location that important to identify to get the most exact GIC. Any questions? Okay.
On your larger systems, it does have any physical resemblance? Like, was it over the United States at all, or is it like a IEEE random system?
Can you say again?
Yes.
Oh,
So
sorry,
on
I
your
can't
larger
hear.
System,
Larger system?
yeah, on like slide 14, you're going through the larger systems result.
Slide 14? Okay. Okay.
Yes. Was that larger system a real system, or was it a fictitious system?
A fixed station?
Was it a fake system?
Oh.
Or a real life system?
It's a real system that is modeled in it's a real system that is modeled in power.
What does EI stand for? Eastern.
Oh, Eastern?
Eastern.
Interconnect.
Interconnect, right?
Interconnect.
American Eastern Interconnect.
Okay.
That's
Yeah.
EI.
Thank you. I tried to search it on Google, but I couldn't figure out.
Got lots of interesting things. You could have asked me on that one. Eastern Interconnect of North America, so it's a real system.
Okay.
Okay. So my question is, did you notice that the substations that were highly sensitive, were they at network boundaries or physical boundaries, like next to a Great Lake, or?
Oh, yeah. I'm sorry. I don't. I don't have the information about that. Like, I haven't got anything about that. Yeah, okay. But I can try to do that.
So
I don't think we looked, Trevor, but they were like all over because it was quite high.
Okay.
But we just checked the highest ones, which would have been at the boundaries.
Okay. So if you had any intuition on why those were the highest, why would you say those ended up being the highest?
Oh, you mean like the geometric of them, like why those substations?
Like, why did those happen to be the most sensitive as compared to another one that wasn't?
Yeah. I'm sorry, I didn't look at that, but I'll try to figure it out and give you the answer.
I think what the mention is it has to do with the linear resistance. So clearly the ratio, like probably in that location, the signal equivalent resistance are higher or lower, so which depends on the relation. It just has to do with the local signal equivalent.
Okay.
Yeah, I mean, probably we went to the equation very fast at the beginning on the. Can you go back to the? Yeah, this one. So like we can find this one to be the normalized variation. So if the local signal equivalence resistance is higher, then the normalized variation will be lower.
Okay, cool.
Somebody else must have another question.
Go to slide 13.
So
So when you assumed the like the model for the buses that you didn't know, did you look at like how sensitive your results are based on like how like what assumptions you made?
Oh,
Like are there specific like I don't really know
yeah.
what the parameters are in this model, but like are there some parameters that are like this the result is really sensitive to?
So the crowding resistance on based on the value of them based on the configuration of the substation and the soil resistivity. However, we don't have the information about the soil resistivity. That's why we can only rely on the substation configuration, which is the voltage level and the size of that substation. Yeah, I mean the problem of we cannot get the precise value of crowding resistance. The main reason is about the soil and thing. It's really rely on depend on the soil resistivity, which means the type of soil and how moisture it is, things like that.
Question for Uyen?
Maybe it's a digression, but there are substations which have reactance grounding and not resistance grounding. So in those cases, would you account the resistance of that substation to be the grounding resistance to be zero, or would you make an approximation, or how do you go about that?
Oh, the crowding resistance?
Yeah, there are some substations which have reactance grounding and not resistance grounding.
Oh.
So they ground the neutral by a perfect reactor with a certain impedance. So in that case, would you account the resistance to be zero, or how do you go about that? Maybe it's for you to think maybe in the future.
So for those substations that assume to have the perfect earthing, like no grounding resistance.
There is a grounding reactance instead of resistance.
Oh, so you mean like maybe capacitor or something?
A reactor. In fact, an inductor is.
Or inductor? Oh, so then I think it will be assumed as because we don't include any reactance thing, any like not real thing in only the conductance. So if you have
why do you ignore the reactance?
Oh, because this is the DC current.
Yeah.
Yeah, that's why I think it would be like short circuit to the ground.
Yeah, but we're talking about the substation grounding mat into the ground.
Yeah.
Okay.
So not a reactance in the transformer neutral. What Wynn's talking about is you got the ground mat and you actually drive rods into the ground, and they're going to have some resistance associated with that.
Yeah, thank you. Yes.
In a future smart grid, would there be some type of real-time measurement of that grounding situation, depending on the moisture and so forth, or is that discussed, or is that not even on the table?
Yeah. I sorry, I didn't know much about that, but I think those things like will be decided by utility engineering. Like they will do those things about getting the value of the crowd resistance.
Yeah, they're actually testing their substations as they put in communication equipment, some of it associated with the smart grid. So they're getting better measurements because they're going out and they're testing out. A lot of times they built the substation a long time ago and designed it to a certain spec but haven't retested. But now they are putting in communication equipment where you need to know what your ground is, so they do retest it. Other questions for Uyen? Miriam, you must have a question.
I read the paper, I know.
You want to ask her something about the paper then? Just giving her practice. It's just for practice. From a friendly audience.
I didn't practice for this.
Mary, you can call on the student of your choice then.
That would be me.
That's why I'm having you do it. That's Shamina.
Oh, okay. So the crowding resistance is the resistance of the between the neutral point of the neutral point of the substation to the ground. So okay, yeah. So
If you want, there's markers behind the board. You can see it on the screen.
yeah, but yeah, I just oh sorry, I just thinking. So as I said before, the crowding resistance is is designed by the configuration of the substation and also the characteristic of the soil. Yeah.
Why is it so difficult to measure, like, reducing the soil moisture and resistivity? Like, what type of devices are they trying to use now that's improving, getting
Oh.
these?
Yeah. It's difficult to.
Yeah, like, we were talking about, like, these communication devices, right?
Measure, yeah.
So why is it better?
When if you had to drive 2 rods into the ground, how would you measure the resistance between them?
To rot in the ground.
Just like pieces of metal to ground something. Like I put in an electric fence and I pounded in a stake to ground it. Okay, that's a ground. It's just a pole.
Yeah.
Mine was like that thick. I just drove it into the ground. Let's say I put another one over here. How would I measure the resistance between them?
The resistance between you mean like to top of the rod?
Yeah.
So it will be the resistance of this rod and the resistance of the crowd mat between them and the other one.
Yeah, so you just put an ohm meter and measure it. See what it is.
Okay, and that's hard to do, like, before.
Well, it's trying to figure out what points you measure between.
Oh, okay.
Thank you.
So depending on how wet the ground is, that's going to change a lot, right? You take it an average over a whole year, or just if you just measure one day, that could be, it could change quite a bit.
Just say interesting question.
I'm sorry, because I also try to search about why it's hard to get the exact value of the grounding resistance, but it's just all said about it's hard to know to find the ground, like the resistance of the crowd path, I think.
Yeah, I mean it changes with the moisture, but if your mat's down far enough, the moisture hopefully shouldn't change too much. Because I mean they are varied, but yeah, if the moisture level changes, yeah, that'll affect it.
Yeah, I'll try to look at what people, what utility engineer, how they calculate those things, and how hard is that.
And you did a really nice job. That was good. Thank you.
Thank you. Thank you.
Hey, Uyen, is that your first time doing a presentation here?
Yeah. Oh, thank you.